Well, tell us why Levin-Wen is a gauge theory.
I'm going to attempt to do that. So this is joint work with, I should thank the organizers. Thank you for inviting. ICMS is absolutely wonderful as well. This is a second time here. I've loved it each time. And thank you so much for the invitation to speak here. I'm losing my voice a little bit, so hopefully you can hear me. Well, just ask me to repeat it. I'm happy to lose it completely by the end of the talk. Yeah, I have contraband tea here in case I need it, so don't tell. I guess I'm being recorded saying that. All right, this is joint work with Kyle Calgello, who's a postdoc at OSU with me, Lori Jones, a longtime collaborator, Sean Sanford, another postdoc at OSU with me, and David Green, a graduate student. And it's based on, it really builds on some other work that appeared last year in quantum with up here, along with Peter Houston and Anoop Podell, also OSU affiliated within their Anoop's a postdoc with me, and Peter was my graduate student. Lots of people here are going to be on the market this fall. So if you need excellent people, look no further. They're great. No, look there. Anyway. Yeah, so I want to tell you today why Levin-Wen is a gauge theory. Kyle really told me about something really cool last summer, and then I'm going to tell you that. You probably already know the story because you know probably a lot more about this than I do. So I'm going to start with this idea of GSPT, and you can do this thing to it called gauging and end up with the Kitaev quantum double model. So I'm going to be particularly interested in a trivial GSPT. And on the left, so you have a Hamiltonian on either side. So you take a Hilbert space over here onto a Hilbert space here. There's a unitary operator here. And it intertwines a local Hamiltonian on both sides. And what's super cool to me is that over here, you have, and I'm always working on some kind of contractible piece of lattice. You have here a unique ground state, which is, it's actually a product state. So in particular, there's no topological order on the left-hand side, trivial topological order. But over here, you take this state and you push it through the gauging unitary, you get a long-range entangled state. And you over here, if you have G here, you have the quantum double topological order. So that's what's describing it over here. So topological order is emerging through this gauging unitary that's taking a local Hamiltonian to another local Hamiltonian. But nothing in life is free. So there's, while you take a product state here to a very interesting state over here, one might say, if you look at the local operators are really interesting, are, what is the word I use for it? They're, I guess, interesting. They're like entangled. You can think about them as entangled or really interesting. And over here, the local operators are, and I don't like using this word, but they're more or less boring. Okay. So, here this is a 2D spin model. And so you're looking, your local operators here are usually just, full matrix algebras. So local operators here are boring, whereas here you'll see them be very interesting. And so what you're doing in my mind here is you're trading a boring state with interesting local operators, and over here an interesting state with boring local operators. Okay. And the big question that I want to ask today, can we do this for Levin-Wen? Well, it's kind of disingenuous to ask a question that I'm going to answer. Like saying, hey, here's a cool question. Oh, here's the answer. Way to make it look more interesting. Anyway, so that's, I'm going to start by actually saying how this works, because we're going to do something really analogous, okay? And so maybe this is one of the benefits of having this, talk after lunch, so that, if nothing else, maybe you'll get a good nap in and tell you a lullaby. Anyway, so, all right, what is the GSPT? Okay, so we're going to start off with some lattice, and the lattice is going to look kind of boring. It's going to look, just about points on Z2 sites in a plane. And on each point, I'm going to put a copy of CG, or rather, C to the G. I'm going to elide the difference between the two. Okay, so it's just, it's a Hilbert space, and the orthonormal basis is given by elements of G, all right? And on here, you know, Gx on the left, Y operator is LG, Gx on the right, Y operator is RG on each site, okay? So we're gonna call that, this is your Hilbert space at site V. Your total Hilbert space, so HSPT, it's going to be the tensor product over all the vertices of your operators there. And your local Hamiltonian is going to be very local, okay? Meaning at every site, I'm going to have this operator, EV. It's going to be defined to be the sum. I have to remember which way I want it to go. Okay, I'm going to take this 1 over the size of G, summation of G of LG, and they're acting at site V. Okay, that's a projection, and it's the projection onto the states here that have the same coefficient everywhere. So it's fairly easy to calculate that if I take PV and I evaluate it at HV, it's just complex numbers. Okay, great. So that's your SPT. That's what we have there. All right.
Would you use a billion here?
No. G is any finite group. Just finite group in this story. Now, what do I want to say? Yes. So because, so your Hamiltonian is now just the sum of BV over V, and so the ground state, there's a unique ground state, is a product state. And I just take this copy of C everywhere, and that's all you get. Great. It is, trivial. Over here, we can talk about the Kitaev quantum double model. How does this work? So now instead of points, I have sites are hosted on edges here. So here, again, we get a copy of CG, again, eliding the distinction between the two. It doesn't really matter. And now I have operators that are going to act locally as well. Again, H quantum double is, again, the big tensor product over the size HL now, because now we're, rather than at vertices, we're at edges. I'm going to write down 2 types of operators for every vertex. I'll tell you, there's also an implicit orientation when I draw this lattice. I'm always going to orient toward the first quadrant. Okay. So if I have here a simple tensor, and let's write, GH, well, I'll write A, B, C, D. A, B, C, and D here in my group. And I want to take this AV operator, for this is my vertex here. Well, I'm going to reproduce exactly that A, B, C, D, if AB is CD and 0 otherwise. Okay. And then for every plaquette, well, I'm going to write down a plaquette operator BPG. Here's A, B, C, D. And the idea is for G, I'm going to glue in a loop labeled G. That's basically the idea here. And so I'm supposed to get now. Then you have to think about orientations. Here I get GC, here I get GB. Here I'm on the right-hand side, so I get DG inverse, and here I get AG inverse. So you can see that BPG, it's just the operator. Here it's LG, here it's LG, here it's RG inverse, here it's RG inverse. And then my BP operator, again, 1 on the size of the group times the sum of the BPGs. And every AV and BP commute, my Hamiltonian, is minus the sum of the AV terms minus the sum of the BP terms. And I guess I'll just finish this up over here in this little box before I go to the next boards. The thing to consider, the ground state here, again, if I'm on this patch of lattice, it's this unique ground state again. But now it's long range entangled, and the topological order is it's the quantum double, G, or known as the center of vec G or the center of rep G, you pick. For the longest time, I didn't know whether this was a model for rep G or whether it was like, because I'm more familiar with the Levin-Wen model, so I didn't know whether this was like closer to Hilb G or rep G. And The answer is it's not either. It's actually a model for the quantum double. And I mean that in a rather particular way. That's not what the talk is about. You can ask me afterward. I thought it was really cool. Anyway, topological order is that. Anything else to say about that? In the explicit example, if G is Z mod 2, AV is I plus, what would it be? Z on 2, and BP is just I plus XXXX on 2. And so this is just a Tor code, right? That everyone knows and loves. It's really just that. All right. Now, gauging is a way to go from the left-hand side to the right-hand side. How does that work? Is it better upward or downward? I think it was downward was decided was the optimal thing. Which is why I went forward first so that it could be seen for long. Anyway, I'm tall enough? Okay, we'll try that. So how does gauging work? Well, the idea of gauging in this case is going from domains to domain walls. Okay, what does that mean? We start here with A, B, C, D. I don't know if this was how I labeled them before, but I look at A, B, C, and D. Really, I can think about these points in my SPT, replace them with little loops labeled by A. This one, I guess, is D, C, B. And they're going to grow until they look, and I'm going to make the corners look kind of square, but really they're round, whatever, doesn't really matter. A, B, C, D. And now I can think maybe there's like little punctures living here so that, looks like that. And now you're going from things hosted on points to things hosted on edges, right? So that's what's happening in this gauging map. Instead of the degrees of freedom being on points, we live on edges. And so if I have this simple tensor, A, B, C, D, it should map to, well, just read it, AB inverse. Here it would be DA inverse. Over here, it's CB inverse. And over here, it is, if I get it right, DC inverse. Okay, and that's what should label each of those edges that we're quote unquote converging to here. Just expand those loops. Right?
How do you know the order of the multiplication?
Because I read, I look at the orientation and I read left to right along that orientation. This is A, but this is now inversely oriented, so it's B inverse. So A, B inverse. If I'm looking this way, I read left to right. I see D going with the orientation. I say A going against the orientation. So I have DA inverse.
No, vision of the red.
The orientation of the red line.
Oh, okay, okay.
Tells me what I'm supposed to do.
I see.
And if I change the orientation of the red line, I'd write down something else, but then I'd probably write down other operators. And all this is choices, individual preference, really. So, okay. So this is the map. Let's make two observations. It's that if I take here a simple tensor, in HSPT, it maps to a simple tensor over here in H quantum double in the image of all the A terms. If I look at my AV terms here, they made sure that AB was equal to CD. Manifestly, this is true. DA inverse times AB inverse is DC inverse times CB inverse. Yeah, if I product these, you get DB inverse. Same thing over here. So I'm already in this image of the PA. Okay. Now, the second observation is that the gauging map is G to 1. Why is that? Well, I've only used the left multiplication, but I could also use the right multiplication here. So if I did the right multiplication of my operator BV acts on the left, that's going to commute with actions on the right. So if I put a G on the right of all of these things, what happens here? It'll yeah, basically, there's no change. It goes to the same place. Why? I mean, you can just see it. Here, this would be AG times G inverse B inverse, which is the same thing. Okay, so it's G to 1. So what we do is we take the G invariant subspace HSPTG, and I have my gauging is now a unitary onto the image of the A terms inside the quantum double Hilbert space. And so you might call this the gauge constrained subspace. And if I conjugate by this, it sends BV to BP by add. Okay. Because now what was at a point is now at a plaquette. And one checks. That's what happens. Okay. Yes.
I might have expected to see a three-phase cycle on the group appearing once transgression. Can you add that to these pictures?
That's an interesting thing that there are other models. This is a very, I'm keeping it, doing the trivial GSPT.
Okay.
Rather than doing some kind of twisted GSPT. And so I'm gonna, this is just the easiest version of this to get us where we want to go. Okay. Now, the last thing to point out about this is that what are the local ops? On the left-hand side, I have the G invariant functions. Yeah. And these correspond over here with basically the local operators over here are the PA compressible matrix algebras. And so that's what I mean by taking very interesting local operators, because they have to be G invariant operators, to kind of boring operators. All right. So now we wanted to take this and we want to go to the context of the Levin-Wen. So we want it to work for all unitary fusion categories. And if you want something to work for everything at the same time, well, there's not much that you can always work with for every unitary fusion category simultaneously. You don't have a lot at your disposal. And if you're going to do this, I like to joke that I've been working with Corey for so long that I have a little mental model of a little AI Corey that kind of tells me how I should go prove things. And AI Corey told me, well, if you can do this, it should involve 4 things. You should involve the tube algebra, the canonical Lagrangian algebra in the center, graphical calculus, and maybe the Oneida lemma. That's basically all you have to work with. The semi-simplicity rather than the Oneida lemma. It's the same concept, essentially. I'll just say that for semi-simplicity. Whatever that's supposed to mean, that's how I think. So, I was talking about this with Kyle, and we're seeing these loops, and this is the fusion algebra of, say, Hilb G, right? This is one way to think about this. This is just a fusion algebra of Hilb G. The fusion algebra is a corner of the tube algebra. So maybe the thing that is going to replace G should be the tube algebra. So let's go with that, okay? So idea, so C is just a unitary fusion category. The idea is replace G, our symmetry group, with this thing T. I'm going to write TC, which is the tube algebra. C, I'm just going to write TC because I'm going to write it a lot, okay?
Isn't it that the tube algebra of Hilb G is the Drinfeld double?
Yes. Yeah.
So isn't the analog more the Drinfeld?
Well, the Drinfeld double, and the Drinfeld double is a Hopf algebra. That's really nice, and that's also something that can act in Hilbert spaces. But we're not going to be so lucky because we're not always going to have a fiber functor for my unitary fusion category. So we're not always going to get a Hopf algebra, or even the tube algebra isn't even a weak Hopf algebra, unless you do some things Morita equivalent to it. So, but the tube algebra is a nice canonical thing. It's something that people like me have grown up with and we know and love, and so that's what we're going to use as our replacement.
I thought it's a more direct analog of DG rather than G, isn't it? I mean, it's
Sure.
literally DG.
Sure, but the tube algebra action we're going to get is going to factor through the G action. So my construction is going to reproduce this story completely for groups. So hopefully that'll assuage your concerns. Is that okay? Where am I? Oh, telling you what the tube algebra is. What is the tube algebra? Yes.
So when you say local operators, that's some kind of preferred local operators, somehow still preference.
No, I mean, here you're doing SBT, you have a G symmetry. And so what are the local operators of this theory? They should also respect G. Okay, and over here, you're only getting this gauge constrained subspace, right? So you want your operators to preserve that subspace. It's not, I'm not really making a choice here. I'm just saying, what are the natural things that you would consider on either side?
Possible to extend them up to twisted sectors?
Yes, you could do that, I think. I don't exactly speak that language, but I think so. And this will also be a way of doing that. Tube algebra. What is the tube algebra? It's the set of things that look like this. Well, it's really the span of things that look like this, where A, B, and C are in. I'm going to take a note out of Theo's book. I'm going to call it pi naught of C instead of air of C. C is X. Sorry? C is X. C is C. Oh, C is X. Yeah. Different levels there. Okay. That's the tube algebra. This is a finite dimensional C-star algebra. What is the multiplication? You stack things when their labels match, otherwise you get 0. And then you need to do something where you sum over orthonormal bases. So you sum here over Z alpha. Really, you want to think about this as something living on a tube. So that the name is not such a clever name, because that's what you're doing. So you should think of it this way. Okay. Stuff on a tube, how you multiply, you stack the tubes, but then you have to decompose on the sides using orthonormal basis. Okay, great. That's what the tube algebra is. It's finite dimensional C-star algebra. To make these pictures rigorous, this the 3D picture rigorous, you can do it in many ways. You can use, basically you can use TQFT. I'm going to use the language of a categorified trace. And this is work that was that I've done with Andre and James Kenner, where we've explored all of this in nice graphical calculus for things like this. I'm going to use that language because I'm most comfortable with it. You don't, this goes back beyond that. So the idea here is that if I look at Z of C and C, there's a forgetful functor. And I look at its adjoint, which we call trace. And the idea is if you take some objects C in here, the picture you want to think about is that it's living, it's like strings living on tubes. And so that turns out to be a very good graphical calculus for that. If you're more comfortable with TQFT, just think about that, or factorization algebras or factorization homology. Just do what you feel most comfortable about.
You say quickly, how does tensor product in the Drinfeld center when it's presented as a tube looks like?
Question. I'm gonna get exactly because that's gonna be one of our problems. Fiber, we're gonna have to say what happens there. Okay, so here are some facts that I want to point out about this. The first is that if I want to look at Hans in Z of C from trace of A to trace of B, you can think about that as the space of things that live on a tube. We're gonna have an A here, got a B up here, and I think about anything that can go around the back. Okay, so that's just happens to be a fact that strings on tubes satisfies. Another fact is that since F is monoidal, its adjoint is lax monoidal. Which adjoint? I'm taking a right adjoint, but it doesn't matter. Because, well, first of all, everything's unitary and they're unitary adjoints and their unitary adjoints are bi-adjoint always. It's also oplax monoidal and I'm going to use an oplax version of it, but just like, let's just say it's oplax monoidal. It doesn't, whatever. Because that's the thing I'm going to use, so let's do that. So that means that I have a map, canonical map, that goes from trace AB to trace A, trace B. I'm just not going to write the tensor signs because I just don't have time. Just don't want to, I'm lazy. Okay, so this is a canonical map. I don't know, you could call it like mu AB and it satisfies really nice coherences, but again, TQFT will give you the same types of stuff. All right. So that's another fact. And then another fact. This fact, I could have said 1, 2, 3. Fact. One of the reasons the tube algebra is so important is that its modules, jumping the gun here, modules for the tube algebra is equivalent to the center as C-star categories. Okay. This is right modules here. Right modules for the tube algebra is the Drinfeld center as C-star categories. But modules for the tube, I told you the tube algebra wasn't a weak Hopf algebra. There's no co-multiplication. So what's the tensor product? As Vincentus is asking, how do you tensor product? All right, well, how does this actually work? If I have something in the center here, maybe I think about it as a wavy line, it maps to, there's ways you can think about it, C of X to forget Z. X is the big direct sum over C and pi naught C of C. So this is just, I take up all the simple objects, I add them up, I call that guy capital X. All right. Hom from X to F of Z, that is, that's what it goes to as a module, because because of looking at fact 1 as this, together with what my tube algebra pictures look like, in fact, TC is none other than end of trace X. So how does it act? It acts by precomposition. This algebra acts here, and actions by precomposition are right actions. Okay, and this is a very Yoneda thing. You're mapping into it, so that's where maps go. So I'm using the tube algebra. I'm using the Yoneda lemma. Life is good. Yeah. All right, I'm doing what I'm supposed to be doing. So also note that this top thing here, it's also equivalent to Z of C from, sorry, I didn't do this part, yeah. I have to do this. This is what I have to do in order to have TC acting. Trace of X to Z. I'd already passed it through the adjunction. Okay, so now you can think about this as a set of maps here that go from the tube, my X string, to, oh no, Z is blue now. Z lives up there, and I do a little wavy line because it's like an excitation, so it kind of wiggles a little bit. All right, and the tube algebra just acts by precomposition. So that's how this correspondence works between models for the tube algebra and Z of C. But now I have to tell you how to tensor product them. How does that work? So because it's a very Yoneda type of thing going on, the tensor product is a very deconvolution product-like thing. So this is one way that you can do this. If I take, say, here I have Y and Z that are in the center. What I do here is this is the space that corresponds to, what is this? This is the direct sum. One way to think about it, it's the, how do I want to write this? I don't have to do it that. I can just write this as follows. Z of C, trace X to Z. I guess I have Y, so I'll put Y. Tensor C of X to X squared. Tensor Z of C, trace X to Z. And yeah, that's basically what this thing is. I should write it actually a little more carefully, where instead of C, I write, yeah, let me write that more carefully because this is important. So you should think of it as the direct sum over A and B and pi naught C of C of A to Fy, tensor C of little c to AB, tensor C of B to FC. Okay, so that's a better way of writing that. I guess C, I have to write C here too. So it's very reminiscent to the day convolution product. Okay. That's how you tensor them. And you'll notice that this is a tensor product. This is not a tensor product in Hill. Because we don't have a fiber functor, we can't just take a tensor product in Hill. Okay. So, great. That's how things go. So now I can tell you what this, I guess we could just say, anyway, that's the tube algebra and what I need about it in order to do this construction of this thing called TCSPT. We'll call it that. It's a fancy name. To figure out what that's going to mean. Yeah.
So in the twisted Drinfeld double case, there's still a quasi-hop structure, I think. Is that always true?
This is not, it's not you have to take something Morita equivalent to it. There's ways that you can do things that look like the tube algebra that are Morita equivalent that do have weak hop type structures. I think it appears in the work of like Frank Verstrata, and I'm going to get other names wrong, but Frank's paper, they do kind of stuff. Yes,
F is your forgetful functor?
that was my forgetful functor. Yes. I got lazy.
The level of generality C doesn't even need to have integral dimensions, right? So it's not gonna be represented by quasi-hop.
Exactly.
In any sense.
This is just any arbitrary unitary fusion category in this level of generality. All right. So what haven't I used? Okay, what's my local Hilbert space going to be? I'm trying to, down here, I've got this thing. I mean, you can't really see it. Let me push it up a little bit. I'm trying to mimic this idea of taking these loops and growing them in order to domain walls. That's what I'm trying to do here. And here, this is looking like a corner of the tube algebra. I have an action here on one side, two actions on both sides. So I should afford an action of the group algebra instead of the whole tube algebra. What I'm going to do is let HV be the following space. And what is this? This is Hom in Z of C from trace of X to trace of 1. Okay. That's what that is. This Hilbert space right here. Okay. Great. It has a tube algebra action on the bottom. It doesn't have a tube algebra action on the top. Okay. What is this space when C is, you're not supposed to write in blue, is that right? All right.
In blue, it's just we can't see it.
When C is filled G, you'll notice that the labels on these strings have to agree. This is a group element, same group element. There's no group element that can split into two and have it cancel with each other on the back. This HB is just CG, or rather C to the G, right? Again,
It's better than green.
What?
Blue is better than green.
Good, because I didn't want to have to carry another chalk anyway. All right. And C is Hill G. HV is CG. So I'm recovering exactly the representation that I'm meant to. I have exactly the ingredient that I want. Okay. And the action of tube factors through the TC action factors through the fusion algebra through C of G. It's good. That's great. So now I want to take my local operator BV. BV is going to be defined as 1 over the quantum dimension of C, summation of DC times C. This is the Kirby element. It's also equal to, well, again, the categorified trace was an adjoint, so there's a unit of that adjunction. So I can say I, this is the unit of the adjunction here. And I can put IDAG below. It actually is this. It factorizes through chopping this, and like this is a well-known TQFT fact as well. And it's, if I have a sum by this regular element around a tube, it chops the tube in half. Here I'm just saying it works so unitarily. Okay, I guess that's probably already known too. Anyway, this is true. You can show it. I mean, they're both elements of the fusion algebra. They both have the correct the same eigenvalues with respect to action by every loop, and so therefore they're the same. They're both projections. So there you go. Yeah, so it's that. You know, what that tells me is that if I take BV acting on HV on top, what happens? I close this up. I use isotopy to move it around. I have a map from X to the unit. There's only one of those up to scalars. This is just complex numbers. So it's trivial. Great. Now, the only problem I have is how do I take a tensor product? Like what corresponds now to putting them at different points in the plane, right? That's a non-trivial thing. I can leave that here, push this up.
I think I don't understand your equation. BV of HV equals C. Do you mean image of BV?
Yeah, the image of BV. BV is an operator. It's acting on a Hilbert space. It's just the complex numbers. This is the image, yes. I should write isomorphic too.
Dimension minus 1.
I got that.
I don't know if that helps or not. Okay, so how do you do this? Well, I want to, let's see. What I want to do is I want to put them in space like this. I want to get, you know, some kind of thing where I'm taking my representations. I want to put them at points in a lattice, Z2 points. I want to have something that looks like this. Does it make any sense? Let's try to figure out how to make it make any sense. So this is me putting these HVs at points in a Z2 lattice. Yeah. Okay. What are they? They're elements of mod TC, right? This is an object in mod TC. Mod TC is the center. It's a braided tensor category. It makes sense for me to put objects at points in a plane and say there's a well-defined tensor product over points in a plane, because braided tensor categories are they're an algebra for a certain kind of operand. Okay, so it makes sense to do this, but I have to use the tensor product in the category. So I can't just stick them there in like the usual Hilbert space tensor product. I have to use the tube algebra, the mod TC tensor product. What does that look like? It looks like this. It's like something like this. We have to join everything together. You have to give some rules for how you would do it. All right, so it looks something like this. We call this the spine coral skein module. It definitely looks something like coral. And you're thinking TQFT and you're thinking spine basis for a TQFT. Spine coral, wouldn't that be cool if it's a thing? Spine coral is a real thing. It's a real animal. And we put a picture from the 1870s, not of spine coral, but of some coral that, you know, next to it in the paper just for fun. It was pretty cool. Public domain picture. It's right next to it. but this is the spine coral skein module. And when I draw this picture, what is it really? It's Homs in Z of C from trace X to what's trace of 1? Remember all the ingredients. What did we have? We had the tube algebra. We had graphical calculus. We've got Yoneda. The only thing missing is the canonical Lagrangian. There it is. There's the canonical Lagrangian. In Z of C, such that Z of C, if I take right A modules, it is 1. Sorry, not 1, it is C. That's how you recover C as a tensor category back from the center. So here, I get A, the canonical Lagrangian, to the number of sites. That's my Hilbert space. How does the tube algebra act? It acts on the left by precomposition. So that's what it means to take this tensor product over sites here. All right. Okay. Fantastic. Now, what happens in the case when C is Hilb G? When C is Hilb G, none of this other stuff is there. This is tensor Hilb. Why is it tensor Hilb? It's because this factors again through Homs from trace of 1 to trace of 1. This is just trace of 1 to trace of 1. Homs there. What is that? That's stuff that lives in the copy of rep G in the center that forgets down to the trivial. Stuff that has that via the canonical fiber functor. So literally, this is tensor product in Hilb for this tensor, for this case. So we're recovering exactly what we should for the GSBT. Fantastic. Okay, that's what I have to say. I haven't talked about like the invariant tube algebra invariant subspace yet, but I have to introduce the thing where the receptacle for the gauging map, the Levin-Wen model. Okay, what's Levin-Wen? I'm going to give you our version. Like I'm going to give you the unitary tensor, the unitary tensor category version of Levin-Wen. That's all about like string diagram calculus. It's not really the 6J symbol type of thing that you put on a honeycomb. I'm going to use graphical calculus for this. Great. What's HV? For every vertex, I'm going to have a space now. And it looks like this. It's the direct sum of all A, B, C, D in pi naught of C. Here I write A, B, C, D. This is just Homs. It's the direct sum of A, B, C, D in pi naught C. C from A, B to C, D. And if I remember, the direct sum over all the simples is X. It's exactly C of X squared to X squared. It's just that space. That's the Hilbert space. Great. Fantastic. My lattice, I want to put sites at vertices. I want to be able to get something that looks like a lattice. So I have operators now for every edge. AL acting at site L, this basically enforces that edge labels match. Okay, so we do the same thing that we did before, essentially that there for the quantum double model, you looked at the product coming in, you assumed that that was it ensures it's the product going out. Here we're doing it a little differently. We're just, these labels have to match in order for me to glue it together. All right. Then BP is defined on the image of the projection onto the fixed point subspace of all the A's. I can define what BPG is. BPG is glue a G loop into the space in the usual way. What you do is you draw this picture, but then you basically use semi-simplicity to cut here for the basis and the dual basis, and then you can interpret that as some linear combination of simple tensors. Okay, so that's what the BP operator is. That's BPG, and then BP is 1 over the quantum dimension summation of DC this should be C. So it's a BP C. So that's what our BP operators are. And right, so our Hamiltonian over here, you're just taking the sum over here. Sum over V, BV. Over here, you're doing minus the sum of AL minus the sum of BP as your Hamiltonian. Okay. What did I erase last? I have no idea. Okay. Great. So now comes time to put this all together so that we can write down our gauging unitary. So this work here is building on this other work than quantum from this 2305. There's a result from that work that we're going to rely on. Proposition from 2305 dot, whatever it was, 14068. And that is, if I'm looking at some chunk of lattice here, say on this chunk, and if I want to know, so there's this nice description of the ground state space in terms of the skein module for the category. But there's also a very elegant description for the image of just the A operators, the image of the fixed points for the A operators in terms of the category. That's what we prove in this other thing. If I take the image of PA around here, well, when I'm on this lattice, now that I'm in the image of PA, you can think about all these edges as kind of being connected because all the edge labels match. And I have some boundary, simple objects, etc. So I'm going to call that maybe a way of labeling the boundary by simples, boundary xi. The image of PA is the direct sum of all ways of labeling the boundary of Hams in C from this boundary xi object I get by just tensoring around here to
Which one was PA?
what?
PA was the.
PA is the projector onto the image of all these AL operators. So unfortunately, the Levin-Wen model, the general one, happens in two steps, right? You first do these A operators, you pass to the ground state of the A operators or of this minus AL sum here, and then you define BP. And so in this intermediate space, there's a nice categorical description of this. This is A to the number of plaquettes. Or we have to forget bound, but A, remember, A in Z of C is our canonical Lagrangian, from which we can recover C. And that's isomorphic to, again, boundary xi, Z of C, of trace of the boundary xi to A to the number of plaquettes. So with all of that, and those plaquettes, the number of plaquettes are all in here. So for here, there'd be basically like putting a copy of A and everything here. And if you're thinking about this kind of from the TQFT perspective, you've already kind of glued all the edges together. You're left with these holes. And if you pull them upward, you're seeing an empty tube. An empty tube is that I of one. That's A. Trace of A. I said I, but trace of A is an empty tube. You're thinking about pulling those punctures upward. They are isomorphic as Hilbert spaces. So we prove an isomorphism as Hilbert spaces. Yes.
To be clear, when you write the map or the Hams boundary xi, do you mean we're just tensoring all of them together?
I'm tensoring them all around in a circle. Yeah. And you might say, well, didn't it matter where you started? This guy has a half braiding. So it can go and it can go over, do a little dance and come back to the other side and everything's unitary. So everything's spherical. So it's all okay. It didn't really matter where I started on the circle. It's always the same Ham space. Okay, so it's time for our gauging map. So
A at this point, is it still trace of one? Is it?
A is trace of one. It's the canonical Lagrangian. That's what it is. Okay, so our gauging map happens in 2 steps. So if I look at my spine coral skein module, the first thing I want to do is I want to project where this X, I want to project it to be 1. I want an empty tube there. Okay, so I'm going to go from step 1. I'm going to start with my spine coral skein module, which is Z of C, what was it? Z of C, trace X to A to the number of plaquettes. And inside here, there's a subspace Z of C, trace of 1, A to the number of P, and the number of plaquettes, or the number of vertices, I guess the number of sites. The sites there are going to match with the plaquettes here, so I'm just going to write number P. I'm already kind of showing my hand, but I should be at this point. So first, I want to make this label 1. But what does it mean to take the invariant subspace? It means you want hums from 1 in a category. So inside here, there's another subspace. I want 1 in Z of C to A to the number P. This one is my TC invariant subspace. Again, if it's the group, it's exactly the G invariant subspace. Okay. And it's actually quite cool why it is. It's like capping this off here. And that's where if I did a global G action everywhere, I could use a recabling and then I'd get 1 G loop and then it goes away on the bottom. So it's a beautiful skein theory argument to tell you why that all works. Okay. Now I want to go over to the, I got to finish. So let's do that. In the second half of Theo's talk, he will say how it all works. So, okay. So now, so I want to go over here on this image of the PA term. I'm at here. Like, I'm all flustered now that you're here. Okay, so I apply this. All right, great. What do? You just apply a junction. You use unitary junction here. This is C from X to FA number of P. And you'll see that now the boundary here, it's like I'm making all the boundaries. I want all the external boundaries to go away. Okay, I'm just projecting them all to be 1. I'm basically making them ghost edges in my lattice model. So that in here, this is C of 1 to FA number of P inside there. And this is isomorphic to, in fact, if you think about what happens when I project from 1 by putting the cap there, this is the same thing as applying a final external plaquette operator. Once I've made all these 1, it makes sense to apply a final plaquette operator to the end to make it now on a sphere. Okay. That actually like kind of glues a little disk around the back here. And so what you end up with is exactly the image of PA modulo spherical isotopy. And this is now on a 2-sphere. Okay. So and one checks that it lines every operator BB, which was this thing. The chopping the tube into a cup cap. These things line up on this side with there. One checks that. Thank you.